Hello everyone, and thank you so much for joining for today's presentation. My name is Philip von Holzen. I work for the company StressHead. It's a big pleasure to have you all together today to present you our CarboStress system, a post-tensioning system based on CFRP materials, and especially looking today how the system can be used for strengthening bridge structures. Very quick, what will we discuss today? First, we will talk about why structures overall need to be strengthened. Afterwards, of course, we'll learn the basic of our active tensioning system, CarboStress, and how it's installed. And then on third point, biggest part of the presentation will be case studies. We will see project where we have used the system to actively strengthen the structures. And on fourth place, we'll quickly talk about some research and the development. And at the end, we'll have time to respond all of your questions. So let's straight start why structures overall need to be strengthened. I think those are all pictures or cases that you are more than familiar with. Starting with increased traffic. Nowadays, cars get heavier, whether it's just bigger trucks or as well the electric cars, which are easily 10 to 30% heavier than their usual cars. So bridges may suffer from insufficient reinforcement, whereas strengthening with external post-tensioning and especially CFRP can replace this missing force, and as well afterwards the structure meets the new requirements. And as well, leading to this, we have often flexural problems. This main problem is that we have higher traffic areas with risk of the structural failures, whereas as well active tensioning solution can prevent and improve or prevent afterwards failures. Other pictures that we often see in bridges is that we have corrosion concerns. So we don't have the internal reinforcement doesn't have anymore the cross area of the reinforcement to really compromise with the strength. Whereas strengthening afterwards these type of structures with CFRP is a great solution, as FRP is non-corrosive and chemical resistance, and it's even better as we apply them on the surface. We don't have to worry after the installation of corrosion problems itself. And of course, the picture that we all know, structural damages, as we can see it here, this truck which crashed against the bridge and damaged the reinforcement, where again, post-tensioning solution can give back this missing force to the structure itself, that again, we can use these type of structures for the next 10, 15, 20 years. Talking today about the post-tensioning solution based on CFRP materials, I would like to highlight the benefits of doing so against strengthening with steel. Steel is an amazing construction material. I absolutely don't question that, although using it as an external post-tensioning system has some down points. Starting with the weight, FRP, for those of you guys who have already worked with CFRP, is very lightweight. So it's not only good for the installation process itself, that it all can be made by hand, but it also means that we don't add an additional load to the structure by installing the system. Then also we have a much higher strength to weight ratio itself in FRP. And as I just mentioned, CFRP is corrosion resistant. So it's very great as we apply it on the surface of structures, whether below a bridge, on the beams or on pier heads, that after installation, we don't have to worry of corrosion problems. And all this leading to a very easy installation due to the low weight and fast installation. We don't need any access or heavy machineries, which often we don't have access, which is great with strengthening structures with FRP. Now let's talk of what is actually the difference between an active strengthening solution and passive strengthening. Now, passive strengthening, as we can see, very great. It's very quick and uncomplicated to install, as you just have to bond these plates to the surface. This although means that the structure needs to be add an additional load to finally activate the support of this plate to the structure. So we do need an additional or deflection of the structure itself. Whereas on the other side, as we can see very clearly here in this picture, the difference, as it says with post-tensioning solution, is that we apply an initial force to this plate, anchor the force to the structure, and can therefore increase the utilization of the plate or the capacity of the plate itself. Now, in summary, the post-tensioning solution provides an active reinforcement as we may put these plates under tension and therefore can reach much higher reinforcement of the structure itself. Now let's talk a little bit more about our CarboStress system itself and very brief as well about the company StressHead. We have been established since 1999, so you can see we have almost 25 years of experience with post-tensioning CFRP plates. We originally come from Switzerland, but we will see this in a couple of slides. We have partnered with Sika and therefore as well got the opportunity to have projects internationally. And here to the right, this graphic should give you an idea how we operate. So the idea is that in a very early stage of a project, we help the engineer, the owner, the consultant, how the system can be implemented to strengthen the structures, whether with drawings, with technical information, as well with the knowledge that we have gained from former projects. And on the other side, we really as well go to the job site. We help and train the contractor to install the system correctly, that we really give back this missing force to the structure. Now, just to give as well here a quick overview, of course, over the last couple of years, we have had a lot of projects in Switzerland itself as well. We start more and more to be active internationally. We just strengthened our first project in Latin America last year due to a change of use. We'll hear a little bit more about this project in the references. And earlier this year, strengthened here in Israel this gas tank due to a safety reinforcement here of the foundation in the bottom section. The system itself can not only be used for bridge strengthening, as we can see it, we can also use it for strengthening industrial and high-rise buildings. Often as well, we use it for seismic upgrade. And as we can see here in the last picture, we're also able to install the system in a round shape to actually reinforce all type of circular structures, such as, for example, silos or water tanks. Now, the system itself has the same idea as a common post-tensioning system. That means we have on one side here a dead anchor, and on the other side of the system, we have this movable or tensioning anchor, which allows us to apply this post-tensioning force to the plate. Now, I mentioned the partnership that we have with Sika. You can see this here. Our plate, the tendon itself comes from Sika. It's the CarboStress S626. You can see here as well the width or the dimension of the plate itself. And our innovation in this system, you can see it here in the circle, are those heads. We call them StressHead, as well the name of our company is, which we press mechanically onto this plate and allow us to transfer the post-tensioning force from the plate itself over this anchor into the internal structure. Now, to actually tension the system, you can see we install a standard hydraulic jack behind the movable anchor. Now, by expanding this jack, we pull back the head, which is here attached to those two threaded rods, which finally leads to giving us this tensioning force in the tendon itself. As I mentioned, from there, the force is transmitted over the head to the anchor and finally generates us here this additional bending moment in the structure. Now, a very important number is here those 50 kip or 220 kilonewton. This is the final force which we can apply to every system. Now, of course, if we need a higher post-tensioning force, we can install several systems next to each other, or as well, as you will see, we can stagger them one over the other to give back a higher force in a more localized area. Now, I think this is pretty straightforward. Now, the question that we have to ask ourselves always is, how can we actually introduce the force in the structure? For this, we have several standard anchors. The first one here, what we already saw, consisting sort of from a shear pin, we mainly use to reinforce concrete constructions. So the idea is that we first make a core drilling of 44 inches in the concrete. After making this core drilling, we can here insert this pin into the drilling. And the idea is afterwards that this pin transfers the whole post-tensioning force into the structure. Now, of course, depending a little bit on the thickness of our structure itself, as well as the compression force of the concrete, will depend how deep we have to make this perforation. To give you a rough idea that we can apply the full force of 50 kip in a concrete with a compression force of around 3000 psi, we need to make a perforation depth of about 8 inches. In case that we only have or can only make, let's say, a perforation depth of 6 inches, because we may have some active span cables here in the concrete, we can as well just reduce the tensioning force to, let's say, around 35 kip, and again introduce the force without damaging the active reinforcement. On the other side, this is an anchor we mainly use in building strengthening, especially reinforcing vertical walls of masonry. The idea is that we make 2 drillings through the ceiling and have the anchor plate on the other side of the slab. This gives us the advantage to introduce the force first into the slab and afterwards already in a much wider area into the masonry, which gives us the advantage to avoid compression problems with the much lower compression force of the masonry itself. And of course, if we strengthen a wall from the outside or a building from the outside, we could just pass the plate on the facade. Let's say we strengthen a stairway. The only thing we have to do is make local perforations. We can pass the system through those perforations and finally post-tension the building over its full height with one single plate. And as well, in these type of projects, the big advantage of the system is it's lightweight. So we're working inside of existing structures and where we often don't have access for heavy machineries, which is no problem as you can install and tension the whole system easy by hand. Now, to give you already an idea, the system has a big benefit that we can as well design special or project-specific anchors. For example, to the left, we see an anchor that consists of the same idea as the one with the shear pin. Although in this project, we were not allowed to make this perforation of 44 inches because we had here to the left and right of the anchor existing span cables that were very close to each other. Now we redesigned this anchor, and as you can see, we worked with 2 shear pins, each of them only about a diameter of around 2 inches to introduce again the force without drilling here in one of the existing span cables. Because of course, if we strengthen the structures externally, the idea is not to harm or damage the active reinforcement itself. Or for example, as well, to the right side, we have an anchor which allows us to introduce the forces with just having the access on one side, for example, when anchoring into foundations. So the idea is that we make a vertical drilling for the system itself and under about 45 degrees, a second one to block here the threaded rod and create here kind of a mechanical lock, introducing here the force now in the bottom in the foundation and only need where we only need access from one side. Now for the installation itself, first, of course, we have to define the exact location of the anchor. Then depending with which anchor model we work, some drilling and chipping work is needed. And as soon as this is done, we can start to install the anchors. Now, as soon as all the anchors are installed, we can start with the installation of the CarboStress system itself. Now, I mentioned earlier that the difference between the active and passive tensioning system is that the active transfers the forces over these anchors, and the passive one need to be bonded to the structure that they can support it. That's absolutely right, although we still as well recommend always installing the system bonded. We can see it here, it has several advantages. First, of course, it gives additional strength and stiffness to the structure, installing it bonded. But afterwards as well, it's a very good mechanic protection during the tensioning process. Now, what does that mean? You can imagine that while tensioning, we have a movement of the plate straight on the surface. Okay, if we strengthen the bridge of the concrete, which could damage the plate itself if the surface is not completely edge-free. Now, with applying it with, in this case, epoxy, we protect the plate exactly during this tensioning process. So the idea is that we strengthen the system before the curing time of the epoxy, depending a little bit with which epoxy and the temperature that we install it is around 1 hour for the curing time. The installation tensioning process takes place in around 20 minutes, so we're absolutely fine with this. Now, as soon as we have applied the epoxy on the whole length, the idea is that we immediately start with the installation. Now you can see here a time lapse where we install it on a bridge. You can see the whole installation can be made by hand as well under working conditions, which we will see afterwards in the case studies was very important to the client. Now my colleague Marcel is here on the other side in training the contractor. Now I just came up here. We really go to the job site and help and train the contractor to install the system correctly. Now we just started tensioning. You can see we make safety steps, meaning we don't apply the full force at once. We review the system itself, the anchor, but as well, we check the structure around the anchor where we introduce the forces that we don't create here additional or new cracks by introducing this additional post-tensioning force. And that's already it. It's really very fast. Finally, as well, that you have a better understanding how this force is applied. We have here a very close view on the movable anchor. Now the system is here inside of the anchor attached to those two threaded rods. Now, as soon as we start to apply the force, we pull back this head, which can be seen very clearly with this distance between the knot and the back of the anchor, which is getting bigger. And of course, we have a manometer on the press where we can exactly measure the pressure that we are applying. And as soon as we reach the required pressure or force to the system, we just have to tighten those two knots and the whole force is in the structure. So it's really a very fast and easy solution, but with a very great effect to the structure itself. Now as well, a big difference between strengthening with CFRP, or in this case with the CarboStress system, and doing it with classic steel solutions, is that with steel you have always a slip behavior and creep in the system. We'll see this as well at the very end of the presentation, but I would like to already mention it here that the system has a big benefit that we don't have any tensioning losses in the system. One reason is what I mentioned earlier, that this whole force transmission between the plate and the head is mechanical, so we don't have any glue. Here we can actually see it in between those parts. The other reason is, you can imagine when we tighten here those knots, we don't have the same slip behavior or mechanism to attach the forces to the anchor, and as with the span cables, so we have to over tension them and then they slip into to fixate themselves. When we tighten those knots on the threaded rod, this won't move afterwards. So are the two main reasons why we don't have any tensioning losses in the system. Now, of course, as well, it's always important to think of if we have to protect the system after installation. For example, on the left side, we can see that we coded them for UV protection and chemical or mechanical damage as well, for example, against vandalism. And of course, similar to classic installation, we as well recommend making safety inspections. It does not have to be so fancy as here with the drones, although it's a very easy solution to just fly there and see, are the steel parts still intact? Is the plate still intact, that nothing is damaging? To really as well identify potential project in a very early stage of the reinforcement. Now, after knowing a little bit how the system itself works and what methods we have to introduce the force and how it's installed, let's jump into some references that you actually get a better understanding how you could use the system in your daily life. First, a quick review. We often use it when we have damages to existing structures, suddenly higher loads, as for example, bridges that have been designed 50, 70 years ago were not calculated with the type of loads we have nowadays with this increased traffic, what we spoke earlier. And of course, as well, if we have corrosion problems, and as the system is free of corrosion, it's a very great solution to as well address these type of problems with the system. Now, the first project that I would like to present you is that one that we strengthened last summer in Mexico. The reason for the strengthening was that a heavyweight transport over 500 tons needed to pass this bridge, and this bridge was not designed for this type of loads. Now, in a very early stage in the plants, we figured out that there would as well be expected had a lot of existing span cables in the bottom section of that beam, which meant that we were not allowed to touch any of this area to introduce the force to the structure. Now, we as well received these informations from the client that we had around 7 feet height of a bridge beam, that we had a flexural deficiency of around 1,500 kip foot, and with this lever arm of about 7 meters. Now, I would like to all of you guys take your cell phone to the hand because I would like to make a quick quiz. So we have those 1,000, around 500 kip feet and around 6.6 feet of a lever arm. What do you guys think? How many systems were needed per beam to strengthen this whole bridge? I'm going to give you a couple of minutes to make some calculations to have an idea how many systems were needed. I repeat, we had a missing force of around 1,500 kip feet and a lever arm of about 6.6 feet. What do you guys think? Okay, we have a first anchor, 2 to 3 systems. So 2 people already participating, saying that we need 2 systems. Let's see what the other people think. Okay, third person as well decided we need 2 to 3 systems. 5, everyone has the same idea. Give 10 more seconds for everyone to give their vote. Okay, let's see how many systems we actually needed and who was right. If those 5 people with 2 to 3 systems were correct. Now, the calculation that we initially made was we divided our missing moment divided by the lever arm. This gives us around 220 kip. Now we took this number, divided by the final force that we can apply to the system, which is 50 kip, and we see we figured out that we need around 4 to 5 systems. So sorry guys, the ones who decided to take 2 to 3 systems, unfortunately, were wrong. Now, with this number, we were as well able to make a first cost estimation, how much this reinforcement with the system would cost, and we're able to convince the client to move on or proceed with this solution. We afterwards, in a more detailed calculation, figured out that we were able to strengthen the bridge with each beam with 4 systems. And you can as well see that we designed here one special anchor which allowed us to attach 4 systems at the same time. And I mentioned that we could not touch any of this bottom section to introduce the forces. Now to do so, we made a similar approach as this one with the shear pin, with the difference that we made a complete core drilling through the whole beam. We then installed this anchor, pushed through this shear pin, which now introduces here the post-tensioning force in the top section. Another big benefit of having here this lever arm is that we also create here a vertical force, which kind of gives or has the same mechanism as when we install the systems in parabolic form to give this uplift force to the structure itself. Now, as well, as you can see, the systems were almost 100 feet long, and we only had very limited access on the very left and right side of each section, which is why a big benefit of the system was its weight. We were able to pass the plate from one side to the other, pulling it over with a rope, could install and tension it all by hand without the need of equipment, which first from the bottom section we did not have access to, and as well space on the platform was not given. As well, to give you, for example, from this project, a quick idea or a basic idea how much the system costs. So we had this complete bridge with 3 sections and a total of 48 systems with each around 100 feet to increase the capacity of around 25%. Now, the material cost itself was around 70%, or around 170,000 US dollars. Then the support and design in this project was a bit higher as we had to design this special anchor, and the on-site and training and supervision was afterwards around 40,000, which gives us a cost of around $5,000 per system of having a length of around 100 feet or different around $50 per foot. Now, the second project that I would like to present you was that one we saw the videos earlier. The reason for this strengthening was that the government bought heavier trains and they needed an additional tensioning force in the bottom section so that the trains could pass. Now, the government already sold the old trains to buy the new ones, which is why it was very important to the client that we did not interrupt with the traffic below the bridge as they were running bus replacements during the tensioning process. As well, in this project is the one special anchor that I already presented. We can see we have had all these existing span cables very close to each other inside of the box girder, which is why we worked with this anchor, which had consisted of 2 shear pins, where we were able to introduce the force here in between those span cables without damaging one. And to give you an idea, here we strengthened 3 bridges with a total of 90 systems in around 3 weeks. And actually, late last year, we went for the 4th bridge, and which had 1 section more. So we strengthened here 1 bridge with a total of 60 systems in around 2.5 weeks. You can see here where the guys install the anchors here on the fixed side. We have the epoxy on the plate, and afterwards during tensioning helps us to prevent any mechanical damage of the system itself. Now, about 4 years ago, we received a call from an engineer from France to strengthen this bridge made out of precast concrete elements. And the reason was that a car crashed here against one of the beams and not only destroyed the concrete itself, but as well the reinforcement inside of it. So that his question was, or the idea was, that we strengthen this beam and give back this missing force to the structure. Now, we decided to install the anchors on the very left and right side of the beam where the concrete was still intact and able to absorb this introduction of force, but meant as well that we did not want to make any drilling inside of that concrete or the beam to destroy the reinforcement itself further. Now we figured out this anchor, which allowed us to install 2 systems at the same time. And the idea was here to introduce the force over a shear bar over the whole height of the anchor itself and having a dimension of only 1 inch in both directions to introduce the forces superficially to the concrete without the need of making any drilling here in the area of the active reinforcement without damaging it. As well, you can see the dimension of the beam was quite filigrane, which is why we decided to install both systems simultaneously, or install both systems and tension them simultaneously to achieve an axial reinforcement during the tensioning process. Further on, of course, before the installation, we installed some carbon fiber wraps here in the middle where the car impact took place. And as well, actually here in front of the anchor to give an additional force to the concrete to absorb the force transmission from the anchor to the beam itself. Now here another project from Qatar. The reason for this strengthening was that a construction truck crashed against this bridge, destroyed one span cable completely and opened the box girder, as you can see, over almost the whole length of that bridge. I can imagine that in this project we needed not only a very high post tensioning force itself, but as well the idea was to give back this force in a very localized area of this missing span cable or destroyed span cable. Now, luckily in this project, we were able to work inside of the box girder itself, and we needed or figured out that we need a total of 16 systems, and to not just spread them over the whole width of the bridge, but to really reinforce that area of the missing damaged span cables, we decided to install several systems over one another. Now, we did so by first installing the shortest system and tensioned it. Afterwards, created an epoxy saddle here in front of the first system, and then installed the second system here on top of the first one, and so on until we had 6 systems over one another to give back the missing force here on the width of around 1.5 feet back to the structure itself. And finally here, a project where we strengthen the bridge in Switzerland due to cracking of a coupling joint. Now this bridge went over, as we can see it here, over several highways, but as well of the public transportation in Switzerland. And the reason was, I mentioned it already, we had in total, or this bridge had in total 4 construction joints, which all started to crack and needed an active reinforcement. Now we decided or figured that we needed to install a total of 18 systems to reinforce this coupling joint to prevent from further cracking. We're able to strengthen all of these 4 cracks that they were able to use this bridge up to 25 years additional. And finally, here where we strengthen not the bridge itself, but a pier head. Now, this bridge in Stegweit in Switzerland was designed or was planned to use higher loads, which although figured out that there was an insufficient reinforcement in the tensioning belt of the pier head. So the idea was to reinforce or apply the system on each side and to give an additional tensioning force to this pier head. We can see how we solve this. So we have the anchor here in the front side of the pier head, introducing the force directly into here, so without damaging the concrete itself. And then installed here 2 systems on each side, giving a tensioning force of 200 kib to reinforce this tensioning belt in the upper part of the structure, that finally they were able to pass here with higher loads or new loads over this bridge. So here picture, we can see we have here the anchor, the system here on the dead anchor side, here the epoxy straight on the surface, leading to strengthen the pier heads. A quick review of all the areas where we can use the system. We can use it for shear strengthening if we have longitudinal and transversal reinforcement, and as well as we just saw here now at the end, also to reinforce the pier heads, which actually transfer the forces from the bridge into the foundation. Now for the end, a couple of words to some research and the development that we run with the system. We work very closely with the University of Lucerne. We have there a lab where we can test any type of special anchor or plate if this is required. We made as well a fatigue test with more than 2 million cycles in the University of Italy. And we have for ourselves a long-term test where we overtension the whole plate or 2 plates 10%. We can see here the behavior. So you have those 2 plates, which are 33 feet long. We started in 2009. So we have here, of course, the behavior. We see more behavior because we have here the timeline of just 1 year, then here the next 9 years. Now, if we take these numbers and extrapolate them in a worst case scenario, which are overtensed to the next 50 or even 100 years, we can see we have less than 2 millimeters of tensioning reductions, which is insignificant to those 2 systems, which are 33 feet long, which is why we can really state we have no loss of tensioning force in the whole system. And I'd like to recap this. I mentioned it earlier. One reason is that the whole force transmission between the head and the plate is mechanical. And as well, the way how we attach the force to with those threaded rod and the bolt don't have any slip behavior. Now, for those of you who are interested, I'm more than happy you signed up. I can send you this whole presentation. We have as well a design concept and a technical documentation that if you guys are interested in further documentation, I'm more than happy to share this with you. Then as well, I would like to mention or engage with you guys to get in contact with us. What do we offer? We always are more than happy to work out a project proposal and a cost estimate. This is all free of charge. We are StressHead is a material provider, so we actually make our money with selling systems and not with consulting itself. So if you have a project or work on something where you think the system could be a solution or you're interested in our opinion, please feel free to reach out. We're more than happy to make your project proposal that you as well have something to present to your clients. And of course, as well, make a cost estimate to give you an idea of the price. To do so, we need a couple of things. Of course, plan some pictures just to get an idea of the project itself. If it's available, any documentation, that's always helpful. And for making a cost estimate, we do need whether it's a missing field moment or the actual tensioning force directly that is needed, that we can determine more or less how many systems will be needed to strengthen the structure. But it's as well like to finish with a conclusion and a takeaway from this whole presentation. Now, the system itself can be addressed to various problems if we have cracking and spalling, if we have insufficient reinforcement of the structure, if we have flexural or shear deficiencies, of course, as well structural upgrade for modern use, or as well corrosion of the reinforcement itself. And some key benefits of doing so with the CarboStress system or a CFRP strengthening solution is that it's very easy and fast to install. And as mentioned often already, it's free of corrosion, which applying it externally is a very great solution. Now you can as well see here my contact address as well from my colleague Marcel. As well, guys, if you do not follow us already, feel free to do so, clicking on the bottom here to join us on LinkedIn. We as well have a newsletter where we post daily or weekly interesting facts about ongoing project, and the newsletter once a month about project in depth. What have we done? How did we strengthen structures? How was it achieved? Just to stay up to date. Now as well, if you guys have any questions, I'm gonna now open for you the option that you can unlock your microphone. Or as well, you can just use the option in the chat. Give me a second. You should now as well be able to directly ask questions. If something is unclear, you can use as well the chat. Please as well feel free to give us here a feedback, scan the QR code. What did you like about this presentation? What do you think we could improve? Or even did we something miss that you would like to have included for a next presentation? We get the first question here. What is the performance of the system in case of fire? Very good question. In case of fire, the system is resistant, or well, not resistant, but against temperature of around 60 degrees Celsius. Now, in case of fire, if we install the system where in a structure, we do think as well, for example, in a parking structure, we do have to protect the plate. There are several coatings that we can apply to the plate until as well, and the possibility to make subconstruction of, let's say, for example, plaster walls to really ensure that the system can withstand temperatures of or times of around an hour, hour and a half, 2 hours, depending on the requirements. We have a second question. What is the approximate strain to achieve loading? Can you explain a little bit more maybe what do you exactly mean with this question, Andrew?
Yeah, just trying to get a feel for the elongation. Say for that 33-foot system, how long did you have to stretch it, or what was the...
Okay. So it's around 0.5% of the length of the plate. Of course, it depends how long the systems are. Usually, installing it in bridges, it's around 1 foot, 3/4 of a foot elongation of the plate itself.
Okay, thanks.
there any further questions?
Okay, I just did a quick little strain calculation, and the carbon fiber from Sika I had must have been a different kind because you couldn't stretch it that far. So this is a different, which carbon fiber? I can't remember. It was projects ago, but I was looking for something extremely stiff, so I might have picked one of those.
Yeah.
Which was the carbon fiber for this one?
The plate itself is the Carbodur S626.
Okay.
It's 6 or 6 centimeters wide and 2.6 millimeter thick. It's similar dimension. It's more or less double as thick. That it as well that we can apply this post-tensioning force to the plate itself.
Okay. Well, that makes sense. Mine was thicker, number one, and I know I was picking a high modulus one so that it wouldn't strain.
That's as well the benefit of the system, that it has very high tensive strength. And as well, the failure point of the system is about double of what we apply. So the failure is around 100 kip, and the failure point itself took always place in the plate itself, so that this additional, let's say, additional material that we apply with this head is even higher dimension, that we have plate failure and before, let's say, slip out of the plate from the head. Robert, you asked what means are available for fire protection of the in-place system. What do you mean with this? Let's see what Robert wrote. Recently, we had a major issue with a fire under a bridge in Los Angeles. So that we have to strengthen now the a bridge. What was that? I get it right. That so if we, for example, in case of fires, we can apply plate coatings to the plate. Exactly, you got it. You figured out yourself. We can apply several coatings to the plate. You can as well made protection mechanisms for the anchors itself. That as well they are whether out of the zone of fire or protected in case of fire. Until as well the possibility that we can make plaster walls, for example, an additional plaster ceiling to really protect the plate. It's not only, it's less the fire itself than the temperature not reaching to the plate in an hour, hour and a half, and so on. And we have another question. Has the system been used to strengthen precast double T systems, such as those in parking garages? I would have to see. Right now, I cannot recall a project where we installed it, but as we saw in the reference, we have often used the system already to strengthen precast structures itself. Often there we have to see a bit how the force can be introduced without, of course, damaging the reinforcement itself. But if you're working on something right now, please feel free to send me some plans, and can more than happy to have a look at and see if or how the system could be used to strengthen those parking beams.
Yeah, thank you for answering that. Yeah, my main concern over there was that precast double Ts. The stems are very thin. They are about 4 inches at the bottom, maybe 3 3/4 inches, and at the thickest at the top they are about 6 inches or so. So not sure if that is too thin to be for the system, but yeah, I'd certainly like to discuss more with you, and if you can get more information, that would be helpful.
Absolutely. Have you been able to write down my email address, or should I send it to you?
Yeah, if you can send it to me, I did not write it down.
Perfect. Sure, we'll do so. Thank you very much for the question. I will definitely reach out to you. We have here the secret F213 exactly. That's the one that we can install or apply this coating to protect the plate itself in case of fires. Do we have any further questions? This was a response. Thank you very much, Juan Capacho, for responding to the question of the coatings. That's the Sikacrete 213F that we can apply to protect it. Do we have any further questions from you guys? Something that is unclear or you would like to ask right now at this moment? And so I can go here back again. For those of you who haven't had time or would like to have further information, please feel free to reach out to me, vonholzen@stresshead.ch. I'm more than happy to respond all of your questions if something is unclear until this moment. If not, thank you very much, everyone, for joining. I hope this was helpful and you learned a new tool that you can use to design. And whenever you come around the project or you think this could be a solution, please feel free to reach out to us and we can discuss together how the system can be used to strengthen the structures. Thank you very much, guys. It was nice meeting you.
Thank you.
Have a great rest of the day and a good start tomorrow then in the weekend.
Thank you.
Thanks very much. Great presentation.
Thank you so much.
Thank you, Philippe. Bye-bye.
Thank you, everyone.